Hello everyone. So welcome to lecture 10, probability and statistics. We will continue with the problem that we discussed last time, this Monty Hall problem. And then we would like to discuss conditional independence. So conditional probability and game of chance. So here we saw an example of Monty Hall. So let us go to that problem. So there was a game show, and the show host shows you three doors. Behind one of the door there is a car, and in other two there are goats. Rules of the game so are as follows. You are allowed to pick a door without opening. Then the host opens a door. The question is, if the host always opens goat door, is it wise to change your door? Okay, so and then we saw a graphical way to solve this problem. So we considered several cases. So so this is the Monty Hall problem, where there is a car in one of the door. You don't know which door, and in the remaining two doors there are goats. You are supposed to choose one of the doors, and then your door is not revealed, and then the host opens some other door, and the host always surely opens a non-car door. So usually it will always it will be a goat door, and then the host will ask you to make a final decision whether you would like to stick with your original choice, or would you like to switch to the other remaining unopened door. So in principle, you have either you are holding a car, or in the other one, or you are not holding a car, that is, you are holding a goat and the other one has a car. So the usual intuition suggests that it may be a 50-50, because either you have the car or don't have the car, and the other one have the car or don't have the car. But the fact that the host reveals the door with a goat, it changes the scenario, overall chance, and so on. So the question was whether you have more probability of winning if you switch, or if you have more probability of winning if you don't switch. Okay, so you can lose in any way, because at the end of the day it's a probability, and you can lose in either way. Okay, but the point is here is to increase your chance. Okay, just like in the prisoner example we saw, you want to increase your chance, right? So we saw this graphical illustration in the last class, where the first possibility is that the door one is chosen by the player. Hello? Yes. So door one is chosen by the player. Obviously, the player doesn't know that it is the car door. Okay. Please turn off your microphones. And in the second step, the host will open a goat door for sure. So host is sure about that. So then this option goes away, and then you are left with this, and then the host asks you to switch, and then let us say you switch. Okay, let us say you made up your mind, and your strategy is to switch, and if you switch, then you lost in this case, because you were holding a car, but then now you get a goat. Okay, so this is a case where you lose. Now you come to the second scenario, where you are holding a second door. Okay, and the host opens the goat door again, and then you switch. So you were with the goat, but now you went to the car, and in this scenario you win. Similarly, you choose the third door. Third door has a goat. The host reveals the goat door always. And then in the third case, your strategy is to switch. So you switch, and then again here also you win. So switching wins you 2 out of the 3 times. Okay. But if you don't switch, then that strategy we all have seen in the last class, right? So if you don't switch, then in this case you are winning. And if you don't switch, then in this case you lose, because you are retaining the goat. And in this case also you are retaining the goat. So here the win chance for you is 1/3, which is less than 2/3. So switching helps. We also saw the exhaustive way of putting all the possible scenarios. So door you choose, let us say is the door one. Let us say price is in the door one. So you do all exhaustive list because it's a small enough example. And the host might open 2 or 3 because 2 and 3 both have a goat. So host might open 2 or 3. But in this case, if you stay, then you win. If you switch, then you lose because price is in door one and you are in door one as well. So you can list out all these possibilities, and even in this fully exhaustive list, you can see that if you stay, then you are like 3/9 chance, and then if your strategy is to switch, then you have 6/9. Okay, so this is again 1/3, and this is again 2/3, which is like greater. Okay, so if you switch, the probability of that you win a car is 2/3, and if, yeah, if you switch, the probability winning a car is 2/6, and if you stay, I think. Okay, so if you stay, then the probability that you win is, yeah, the probability you win. Okay, let me change these things. Okay, the probability that you win is 1/3. Okay, so if you stay, then the probability that you win is 1/3. Okay, so the strategy is that you should choose to increase your chances. You should switch. Okay, and we can also make a decision tree diagram. So we have been getting used to this. So let us say we start the game. Okay, so that's the root, and then from the root you have you had two options. Either you would have chosen a car door, or either you would have chosen a goat door. That's the only two possibilities. So that hence you have only two branch coming out from here. And this is indeed a random choice case here, because initially when you choose obviously randomly. So the probability that you will win a car, okay, if you follow this branch, um, no, I mean, what is the probability that you select the car door, and that is 1/3, okay, because there are 3 doors, okay. So the probability that you end up selecting a car door is 1/3, and probability that you will select a goat door is 2/3. Okay, so that's how you branch, and provided that you have moved to a car door, then if you change, then the probability of your winning is 0, because you were in the car door, and if you change, then you are going to go to get the goat door. So then in that case you will be having 0, and if you don't change, then you retain the probability of 1/3. And similarly, if you follow this branch, then you have with a two-third probability you will pick a goat door. So you may already be in a bias, right? So, and then here, if you change, um, but the important thing here is like, it's not just change, right? It is like you are changing after the Monty has opened the goat door. If Monty would have picked the door randomly, okay, then things will not be same, because then your probability of winning a car will always remain 1/3. Try to prove this. Okay, I will give you. So there's something called random Monty Hall. Random Monty Hall problem. Okay, so I have listed this problem as an exercise. I will leave it up to you. You can work out. Imagine if Monty had opened the door randomly himself, okay, without knowing, right? So then your probability remains 1/3. Okay, that's how you distinguish between what is happening, because the fact that Monty deterministically opens a goat door, okay, that's the main thing here. Okay, so then you will surely, let us say, by your strategy is to change, then your probability is like is 2/3, because you came via this branch where you chose a goat door. Now Monty opened another goat door, so both the options are exhausted now. Now if you are changing, then only car door is left, so you are carrying over the full 2/3 probability, and then you so after this branch onward, you are surely going to get a car. Okay, but until then, you have to pay the 2/3 probability price, right? So you retain 2/3 probability in the end. And if you switch, if you don't change, then you are going to remain in the goat door, because you came via the goat branch and you didn't change. So you remain at 0. So this is also with respect to the tree diagram. So the important thing for you to note is the fact that Monty opened the goat door, and then your other choice. So if you don't change, okay, and if you were in the goat door, then your chances become 0. Okay, so we can apply a Bayes theorem also in the Monty Hall problem. So let us see how we can use the Bayes theorem and conditional probability and so on. So let H be the hypothesis that door 1 has a car behind it. Okay, so H be the hypothesis that door 1 has a car behind it. Like, as I said, sometimes people use H, E to denote a hypothesis or evident, but these are events. You can also use notations like A, B, it does not matter. So H is the event that door 1 has a car behind it, and E is the event that Monty has revealed a door with a goat behind it. Okay, so these are the two events that we define. Then the problem can be restated as calculating P of H given E. Okay, so what is the probability that door 1 has a car behind it, given that the Monty has opened a goat. Hello, please turn off your microphone. Yeah. So then what is the probability that so we fixed on one of the door, like there is nothing like without loss of generality, right? So we pick one of the door, and then we ask for the probability, because the way these goat and car are distributed is anyway random. So there is no loss of generality here. So we can take some door, let us say door 1, and we decided an event on that. And then we are saying what is the probability that door 1 has a car behind it, given that the Monty has revealed a door, a goat door. Okay, I mean not necessarily the same door, because okay, so since every door either has a car or a goat behind it, okay, the hypothesis H complement is the same as door 1 has a goat behind it. Okay, so we can since H is this statement, so the negation complement of this statement is door 1 does not have a car behind it, which means that door 1 has a goat behind it. Okay, so that's what we have written here. So the H complement, how we will construct, that's what we. So there are a few things that we have noted down. So H is the event, E is the event, and then this is the conditional event, H given E, and then we are saying here H complement here. So now the question is like, what are these, right? So we would like to know probability of H. So what is the probability that door 1 has a car behind it, right? What is the probability that door 1 has a car behind it? So how do we calculate? There are 3 doors, right? And one of them has a car, and other one has other 2 has a goat, right? So you can calculate this probability, right? So what is the probability that door 1 has a car behind it? Can you answer this in the chat? So what is the probability that door 1 has a car behind it? 1/3 group. Great. So Sri Arumula replied first. Okay, so I go back to the slide. So this is like 1/3. Okay, so the sample space is like 3, and then out of that 1. Okay, so it is easy, most of you know. Okay, and probability of H complement, well, from the axiom of probability we know that it is 1 minus probability of H. So this is 1 minus 1 over 3. So please turn off your microphone. Okay, so the probability of H complement is 2 over 3, right? And the probability of E given H, So what is the probability of E given H? Okay, so what is E? Okay, so the Monty has revealed a door. So what does this mean in words, right? So what does this mean in words? Probability of E given H. So what does this mean in words? Okay, so the Monty has revealed a goat door. Okay, so H means that the door one has a car behind it. Okay, so door one has a car behind it. Let us say door one has a car behind it, and this has a goat. Okay, so what is the probability that Monty will reveal a door with a goat? What is the probability that Monty will reveal a goat door with a goat, given that door one has a car behind it? So what do you think will be the answer in this case? So what is the probability that Monty will reveal a goat door? Go back to the chat again. So what do you think about this new question that I'm asking? The probability of E given H, what do you think? Okay, so I can write this in the word. The probability of, so E is like Monty opens goat door, given that H was door one has a car behind it, right? Door one has car behind it. So what do you think? What is the probability with which Monty will open a goat door, given that the door one has a car behind it? Anyone? Probability of E given H. So you can ask question by turning on your mic. Okay, that's okay. If you want to ask question, then you can always turn on your microphone. Okay, you are allowed to do that, right? But I cannot allow you the presentation and so on. Okay, control of the presentation and so on. Okay, so what do you think? Like Monty opens a good door, given that the door one has a car. I mean, has a car behind it. Remember, Monty always opens a good door actually. Okay, so I think it will be one. Okay, what do you think? Okay, because Monty always opens a good door. Actually, it's even independent of this, right? So I would say this is one. I hope I'm not wrong. And then probability of E given H complement. What is this? Probability of E given H complement. Now, probability of E given H complement is what? So in words, what this is Monty opens a goat door, given that door one has car behind it. No, door one also has a goat behind it because it's H complement, right? Door one has a goat because it's H complement, right? Now, what is the probability that Monty will open a goat door? Obviously, Monty opens other door, not the same door one, right? Door one is for the player. So Monty will open some other goat door. So what is the probability that Monty will open other goat door, given that door one has a car behind it? I believe Monty will again open a yeah. So Dhruv, you are right. It will still be one actually. Okay, so it will still be one because Monty is deterministic guy, right? And that is why this changes all the time, right? So Monty deterministically open a goat door regardless of what you are telling, what the user is choosing, because Monty always Monty always has a go door option left because there are two go door. So even if the user one picks up one go door, Monty will always get an opportunity to open a go door. Even if the user chooses, if the user is on the car door, then Monty has two go doors. So if you, and he is surely opening always go door. Okay, so this is what we believe. We believe, and these are like not like these are just coming from our observation, right? This is not really um, um, any calculation that we are supposed to do. This is the information given in the question itself. So, so this data is available to us, and what we want. Okay, so what we want is probability of H given E. So what is probability of H given E? Okay. So what is the probability of H given E? So what was the Bayes theorem, right? So recall Bayes theorem. Recall Bayes theorem. So Bayes theorem flips this, right? So that's the main tool. That's why it's known as an important tool, because it can flip this E given H. Okay, and probability of H. Okay, and then divided by probability of E. Okay, that's the Bayes theorem. So you should be very familiar with this by now, Bayes theorem. Okay, so I'm going to make some space for myself. Okay. So, so what do we do here, right? So what are the things given to us? Probability of H is there. Probability of E given H is there, but probability of E is not there. So this is not available. Not available. So in that case, we have to also use the total probability, right? So probability of E given H to expand probability of E, right? So we have to use total probability here. So what does total probability say? So total probability says that probability of E is probability of E given H, probability of H plus probability of E given H complement, probability of H complement. Okay, so these are the things you should now be very familiar with. Now we want to see whether this data is available with us. So E given H is there, yes. Probability of H is there, yes. Probability of E given H is there, yes. Probability of H is there, yes. Probability of E given H complement is there, yes. Probability of H complement is there, yes. Okay, so it seems that all the data is given to us. Let us check whether our answer is matching with the three different ways. One way we solved it graphically, one way we did an exhaustive list, one way we solved it using decision tree, and or probability tree or choice tree. So there are like three types of name. Probability of E given H is 1, and the probability of H is 1 over 3, right? And probability of E given H is 1. Probability of H is 1 over 3. Okay, probability of H is 1 over 3. Probability of E given H complement is 1. And then probability of H complement is 2 over 3. Okay, so what do we get out of this? So out of this, what we get is just 1 over 3, I guess, right? Because this is 3 over 3, so this is 1 over 3. So the probability that, so probability of H given E was what, right? So probability that door 1, what is the probability that door 1 has a car behind it, given that that Monty has revealed, given that the Monty has revealed a go door. Okay. Yeah, there is no mistake here, I believe. So probability of H given E, is 1 over 3. So that is okay. So that also means that it's better to switch. Okay, so can you interpret this? It's not a wrong here. I was wondering what is going on. But so because the probability of, if you stick with the door 1 now, the probability that you will hit is 1 over 3. So switching will make sense. So if you compute H complement given E, then this will be 1 minus probability of H given E. Okay, so let me make some space. I hope we are able to make sense of this, right? Okay. Okay, so what we got is this, right? So probability of H given E is 1/3. So what this is telling you is that you have started with door 1. Like imagine you have started with the door 1 and I mean, we fixed some door, right? Without loss of generality, let us say we fixed some door and it has a car behind it. Okay. And the Monty revealed the go door, and then so what we are asking here, the way we have to interpret this is like what is the probability? Okay, what is the probability that the door 1 has a car? So it's not about like, it's not about deterministic here. We are nothing is deterministic except for the Monty that he is going to open the car good door. So we are talking about probability. It's not given to you that door 1 has a car behind it. We are talking about what is the probability, right? What is the probability that door 1 has a car behind it? Given that Monty has opened a door, good door, it's 1/3. Okay. Now the probability that if you have chosen the go door, if you have chosen a door, and if you are not switching it, okay, then it will remain 1/3. But if I do probability of H complement and given E, then I will do 1 minus 1 over 3. So this is like 2 over 3. Okay, so this is what we arrive using a Bayes theorem. Okay, so probability, and it's about probability, right? It's, do not get mistaken by the it is an event that may or may not happen. Okay, it's an event that may or may not happen. The door 1, so we are talking about probability, but given that so if I switch and do a H complement, then I will arrive at 2/3 probability. So this is another view of Monty Hall, but via conditional probability. Okay, and this tells us that switching should help. Okay, rather than sticking to sticking to door 1. Rather than sticking to door 1, like door 1 was randomly picked first of all. Okay, so now if you stick to door 1, then the probability that you will have a car in that door 1 is 1/3. Okay, that's the way to interpret it. I hope you are getting it right. It's intricate, but it's fine. Okay, so H complement here means like I'm going to switch now. Okay, so I'm going to switch, and then it becomes 2/3. So that's the Monty Hall problem. Okay. Okay. Yeah, this is not random Monty. Yeah, this is not random Monty. So Sri Arumala is saying, is this random Monty? No, random Monty here is like is sure to pick the good door, and this is how we calculated this probabilities. Remember, this deterministically it's coming out to be 1, right? Because of the deterministic nature of Monty. Because Monty is picking the good door for sure. That is why probability E given H was 1. It's like surely, we are completely sure. If it was random, this is where you will get the changes. Okay, so if I change this problem to random Monty, the changes that you have to do are these two. But now that we are sure that the Monty is going to open the goat door regardless of whatever hypothesis you choose, because in this problem Monty always has at least one go remaining to open. Okay, so and Monty knows he is going to open the goat door, so you will have 1-1 in either case, whether the user is sitting on the goat door or not. Okay, user doesn't know anyway, but Monty knows for sure that where is the goat door. So this is deterministic Monty. Okay, so one of you are asking in the chat, no, this is deterministic. That's how we got this 1-1, right? Okay. Yeah, so some of you are also replying. Murli is also replying like that this is not random. Yeah. So some of you are saying like, did we know PE? Well, we know PE after calculating, right? So we have did a total probability, we applied total probability. So in the problem statement, from the problem statement, we know PE because we can calculate by using total probability P of E given H, probability of H, and so on. So we know this because we know the individual terms involved here. Okay. So the concept of dependence and independence, I will introduce this. Okay, we have not concretely defined independence and so on, but we don't need this here. Okay, we don't need explicitly here. Okay, if you see, so Narayan is asking this, right? What about H and E or independent and so on? We didn't need an independent property because independence says that, okay, explicitly in calculations, I'm saying if I need independence, then what I would have wanted is E intersection H is probability of E times probability of H. I didn't need this in my calculation. Okay, I didn't need this in my calculation. This is coming from simple IQ. Like, what is the most troublesome part here was this. In my opinion, the most troublesome part was this. Okay, because probability that door one has a car is 1/3, because this is like some like red ball and two blue ball problem and so on. So what is the probability that I pick a red ball? It's 1/3, right? So this was simple, and this is coming from the deterministic nature of Monty. We did not need to explicitly use any of the independence property yet. Okay, so that's fine. So that's what Narayan was saying. Can we remodel this question as probability of choosing a goat without switching? Yeah, you can do that. Like, I mean, they are complement of each other, right? So Slok Pandey is saying, can we remodel this? Obviously, remodel this. Like, both come naturally, right? So switching, non-switching are complement of each other. So whether you start with a switching strategy or non-switching strategy, one will be a complement of the other anyway. Okay, so that's what. Okay, now let us go back to the lecture. So I believe this is one of the problems where it should clarify your doubts.
Excuse me, sir.
Yes.
Like I was saying, not by complement, but this question is exactly like we are choosing a goat without switching. So both questions mean the same thing, right? If we are getting a car and then we are switching, or we are just choosing a goat, so how is it different then?
No, look, yeah. So look, in this question, our focus. So the way we have modeled this problem is like, we are focusing on winning the car. Okay, so let us say we are focusing on winning the car, and we picked one of the door randomly, like door one. Okay, it doesn't matter, right? So the way we start with this problem is like, the event that we define is like, I am focusing on winning the car, and let us say then I'm the next question I'm asking is randomly, let us say door one, because there is no loss of generality. So randomly I'm saying, let us say door one, then what is the probability of my choosing a door one and having a car behind it. I have not been given a car yet in the door one, because it is never revealed to me. So the way I define an event is like this, like let us say my strategy is to, I mean, goal is to win a car. So I say, okay, randomly, let us say door one. What is the probability that door one has a car behind it? And then I go ahead and then do the calculations. But it may be possible that you define maybe some other event. Okay. So it may be like you can model it based on the goat also, right? So the probability that one has a door one has a goat behind it, but then what you are really interested is the complement of that event. So the door one doesn't have goat behind it. What you need is a car. So if I
Sir,
understand your question correctly, I think we can remodel things. Like it's not a big deal here, as far as I understand. It's just that some calculations will
sir,
change.
like
And
instead of
yeah,
using base, I'm saying like it's
yeah,
another way of solving maybe. So
yeah.
like if we are assuming that we are selecting a car in the beginning, so then the probability is 1/3, and then we are saying to switch. So then we can say like we are going to select a goat out of the three. Then it will be 2/3, and we can get the result. Or is it a wrong strategy?
So yeah. So what claim you are trying to make? Because I didn't get completely. Okay, tell me.
I said like instead of claiming like if we are opening and we are saying that one of them is a goat door and then we are given a choice to switch. So and then we are calculating based on those probabilities. Instead we can say like if we are selecting a car in the beginning, the probability is 1/3, and then we have to switch. Then the probability of selecting a goat is like equivalent to this condition. Like selecting a car and switching is equal to the like is instead of saying this much, we can say that you can choose a vote and then it will be 2/3.
Yeah, I mean, maybe the way you are saying it should also work out. Yeah. Um, I'm not sure there is like distraction coming from your end, but um, it should be possible in many different ways, right? I mean, if you want, then you write up what you are trying to say, okay, and then or in the discussion forum you try to write this. I'm not sure exactly I understood your question, but we can postpone this to the discussion forum, I think. And so like the other way that you are saying, just write up, okay? Write it up, and then we will discuss on that. Okay.
Okay, okay.
Okay. Yeah. So surely write this in the discussion or in the chat, okay? So that we can answer. Okay. But yeah, as I said, like you can model this in a different way. It's fine. Okay. Either way, as long as your logic is correct, you will end up with the correct interpretation. Okay. So, yeah. So there can be problems that are similar to Monty Hall, but you may not see this in the beginning. So if I can show this problem here, it will turn out that this is similar to Monty Hall. Okay, but yeah, but you need to like figure this out. Okay, so what this problem is saying is like suppose we have three cards identical in form, except that both sides of the first card are colored red, and both sides of the second card um, are colored black. Okay, so there is one is black and one is red, and one side of the third card is colored red, and the other side is colored black. Okay, so we have three identical cards. So let us draw the cards. Okay, so in this case, both sides of the first card are red. So this is the case of red, red. Both sides are red, red. Both sides of the second card are black. So this is like the case black, black. And one side of the third card is red and the other side is, so this is like red, black. Three cards are mixed up in a hat, and one card is randomly selected, okay, and put down on the ground. Okay, so one card is randomly selected out of this. Okay, and put down on the ground. If the upper side of the chosen card is colored red, okay, what is the probability that the other side is colored black. Okay, so I hope the question is clear. Like you can take few seconds to understand this question, right? So we have three identical cards. First card, both sides are red, red. Second card, both sides are black, black. Third card, one side is red and the other side is black. They are randomly mixed up in a hat and randomly selected. And one card is randomly selected from the hat. Okay, and put down on the ground. If the upper side of the chosen card is colored red, okay, so if the upper side so for instance, if that is the case, like in the condition itself it told you which are the two options, remaining options you have, right? So if the upper side of the chosen card is colored red, so the red will only come from these two, right? So it is similar to like Monty in the sense like you are surely given a card whose one side is red. Okay, so it will be surely one of these two. Okay, so let us say either let us say RB card came, right, and you are surely shown that the upper side is red. Okay, so the upper side is red and behind there is a black side, right? So if the upper side of the chosen card is red, what is the probability that the other side is black? So what is the probability that the other side will be black? Okay, so it's like either you would have picked this or you would have picked RR, and RR, the upper side is red and the back side is red. Okay, so if you can see, the intuitively it is looking a bit similar to the Monty Hall problem, in the sense that it is similar to Monty Hall problem in the sense like, so what do you associate? How do you associate this to the Monty Hall problem? In Monty Hall, we had a car and goat. So what are what are the counterparts of this car and goat in this problem? Can you give some hint in the chat? Do you, as I said in the beginning, intuition is the most important thing in maths. Rigor is just writing up. But if once you have figured out things, writing is just a secondary part, right? So what I am asking about the planning part, right? I'm not even asking for the answer here. What I'm asking is, how do you relate this to Monty? Like, first of all, is it related? What are the differences of this problem from Monty Hall problem? What are the similarities? Let us say in Monty, I had car and goat, right? In this case, do we have similarities with respect to car and goat, like with respect to color? So what is RB? RB is like red one side and black the other side of the card. Okay, I hope Mehul you get RB, right? So R and B are the short words for the colors. Okay, so one card is with one side red, other side also red. BB is like another card with one side black, other side also black, and RB is like the third card with one side red and other side black. Okay, so someone is saying car is RB. Okay, Mehul is asking car is RB. Okay, is car like playing a role like a RB? Hmm. So is car like a RB here? Yeah, so Slok is saying like, okay, I mean, one thing we can see similarities, like what is the deterministically shown to us, right? So in Monty Hall, what was shown to us for sure was a goat door, right? And what is being shown to us here for sure is the red side of the card. Like red side is always shown, right? I mean, Oh no, is it? I'm sorry. Maybe I'm wrong, right? Um, yeah, so if the upper side of the chosen card is colored red, okay, so if the upper side of the chosen, so it's like given that the upper side of the chosen card is red, okay, so the question that we may ask in the case of Monty is like, given that the Monty is going to open the goat door, okay, so then what is the probability of you winning, right? So there are similarities, and let us see what happens if we write down. Okay, so I'm going to like remove this and try to solve this also with conditional with Bayes theorem, right? So the events are in this case like also clear, right? So so let us write down systematically, right? So let us write down the events, okay, and then we will use the Bayes theorem, right? So let us work out a solution. So solution for this. So RR is the chosen card is red red. Okay, so let us say that RR means that the chosen card is red red, and BB is chosen card is black black. Okay, this means both sides are black. RB is chosen card is red black. And we can define an event R where the upturned side or the upper side, okay, so the card that is picked up and the probability of that card that side being red, okay, so side of chosen card is red. Okay, so if we consider these events, then what we are asking for is probability of picking RB, because that is the case, that is the card we want, right? So RB is like a car, right? Like Mehul said in the chat, right? So RB is like a card because that is the one where the one side will be red and the other side will be black, and that is what we need, right? So RB is like a car, so that is what we are looking for, given that the red one is like is revealed, right? So this will be probability of RB intersection R divided by probability of R, and then we apply the conditional probability, right? So probability of R given RB, probability of RB divided by probability of R given RR, probability of RR plus probability of R given RB. Okay, sorry about that, it's very strange. And then probability of R given RB plus 1 second. Yeah, so in this case, like we are going to apply total probability, like so in this case, what we are going to apply is the following. So R given RB and probability of RB. So you will see that the total probability is, because they are like three possibilities here. So now the total we are expanding this over three cases. Okay, this is the generalized version of the total probability. So R given RB and then probability of BB. So what does total probability tell us? Total probability tell us that you partition your your sample space into three partitions, and this is what we end up doing. Okay, So there are like three possibilities: RR, RB, and okay, BB, right? Yeah, so this is BB and this is RB. Okay, so you don't get confused. So this is RB and this is like BB. BB. Oops. Okay, what I don't like this. This is BB and this is RB. So you see how I have expressed the total probability here. The total probability is now expanded over three different cases. One way is like you take an event and you take a complement of that. So I can express it, expand total probability using that, or I can condition on three different cases, and they should be exhaustive. But I know that they are exhaustive. So either could be RR, RBB, or RB. So they do partition our space, right? So I can expand this in three terms now. Okay. Okay, so I can make some space to solve this problem now. Okay, so let me do this now. So let us fill this now. Okay. So what is probability of R given RB? Okay, so what is the probability that you will get red from a red-black sided card? Well, it is half. Okay, it's a 50-50 because one side is red, other side is black. What is the probability? Okay, what is the probability that you pick RB? Oh, why should I? I'm sorry. There is something. There's some mistake here, right? Because okay, let's see. So what is RB here? No, it seems fine, right? Yeah, okay. So what is the probability of RB? Right? So what is the probability that I pick RB, the card RB? Right? So RB is one of the three cards, right? So RB is one of the three cards. So probability that one picks the card RB, there are three cards. So I would say it will be 1/3. Okay. You can also double check. Okay. And what is the probability that I pick a R given that it is a RR sided card? Well, it is 1 because that's deterministically 1, right? What is the probability that I pick RR? That is 1/3 because that is one of the three cards. And what is the probability that I pick an R given that I have RB? So that is half. What is the probability of picking RB? It's 1/3. This is one of the three cards, right? What is the probability that I pick R given that I have chosen RB? So it's half. Oh no, this was BB. I have mixed things up, right? So this was BB, right? So this was BB. This annotator is really. This was BB, and I'm asking for what is the probability of R given BB? That will be 0, right? That will be 0. So if we do the calculations, what do I get? Right, so this is like 1/6 by 1/3 plus 1/6. Right, so this is 1/6, then 6 is 2 plus 1. 1/3. Okay, that's what I get. 1/3. So this is what we get, and we are almost on time. It's very strange how time goes. I have like 30 slides, but I can go only up to 10. That's very strange. Anyway, like, but these things are important to do. And one of the important thing that I think I told you about total probability in general. So there was a slide where I told you how you can expand total probability in general. Okay. So total probability, because you can partition your sample space in.
The third denominator should be 1 by 3 into 0.
Third term in the denominator. Probability that I have a black, probability that I have a red, given that I have a black, right? So what we are asking for is probability of red, given that we have black. Yes, it will be 0 and okay, sorry, I get your point. So BB, right? Okay, sorry. So indeed, yeah, this will be 1/3. So this is probability of BB is 1/3, and probability that red given RB. Okay, thanks for correcting. Okay. So yeah, so it does not affect our answer still. Okay, it's 1/3. So we have to stop here, and we will do more interesting problems with the Bayes theorem. Slightly more tricky ones, just to like, the more tricky ones we do, more clarity we get. Okay. So we will do more practice in the next class, and then we will yeah, and then we will go into some more interesting things